Okay, so let me start by two procedural issues. One of them is that, this is the week for course evaluations. And they changed, I guess you know it, that now course evaluations are being done online. So I would like you to, for Friday, to bring some devices with which you will be able to do the evaluations online. So we'll do it on Friday, and if you remember, just bring a laptop or a cell or something that you can connect to the internet with. The other thing is that assignment 4, I will upload it tonight. I still have here some unreturned assignment 2, so if you have not picked your assignment 2, you can pick it from here at the end of the class. Yes?
You uploaded the marks for assignment 2 online, but I think that was the link for assignment 1.
So it was fixed or what? Yeah. Both of them are in the same place. It's just a matter of patiently scrolling down. Yeah, okay. Or scrolling. Okay. Okay. So let's start our lecture. So where are we standing in a general problem? The general issue that we're trying to handle is the question of how to overcome the computational complexity of learning tasks. And we have seen, why is this problem so bothersome? Because we have seen that even the most basic learning paradigm, ERM, is in most of the natural cases becoming NP hard to optimize. So since even the most basic learning paradigm is computationally infeasible for many classes of interest. Okay, so the question is, how do we overcome the computational complexity of learning tasks? And if you look at ERM, you can see immediately that this is basically, one can view it, and we did this kind of view when we talked about the computational complexity. ERM is a kind of optimization task. So the task we are facing optimization problems. Like given a sample S and a class H, find the H in H that minimizes some loss, the empirical loss LS of H over H. So this is an optimization problem. We have a notion of a loss, we have a notion of some cost, and we have a collection of candidate solutions, and we're trying to find a solution that will minimize this loss. So those are optimization tasks, and the question is, and these we have seen are going to be, in general, very difficult optimization tasks. So how are we proposing to overcome it? So the major source of computational difficulty of solving such tasks is the existence of local minima. So if I have, we can think of it as I have some space, this is my class H, and I have some loss function that I want to minimize, and from different candidates in H, I get different values of the loss, and I want to find the minimizer, and it turns out that the major obstacle is the existence of local minimum. Because if I did not have local minimum, I could use some kind of a greedy search. I will start with a point and go in the direction that improves the loss and keep going in the direction that improves the loss. But if I have minimum, if I have local minima, which is, and I'm trying a greedy approach, then the greedy approach may get stuck in some local minima and will not converge. So it turns out that this is really a major problem. Once we overcome the problem of the local minima, many of those optimization problems become feasible. Okay, so we went from the task of learning to an optimization problem. For optimization problem, our difficulty came from the existence of local minima, so we want to avoid local minima. And we said that we can, when can we avoid local minima? And that's what we talked about last time. So we defined a way to overcome it. We defined the notion of convex functions and showed that such functions do not have local minima unless these are global minimum. And then we are happy. If we find the global minimum, we don't have to worry anymore. So we define the notion of convex functions. We show that convex functions don't have local minimum. And then we want to apply it to our task of learning. So we would like our, so what are we trying to minimize here? Here we're trying to minimize the loss over a sample or some notion of a loss. So we would like to come up with versions of our learning problems in which the loss is a convex function. And then we will be in a better situation to solve them optimally, to find an optimal solution in an efficient way. So that's where we are. So let us define two notions here. So an optimization. The one thing to note is that the notion of convex functions is restricted to functions over real vector spaces. Because the notion of convexity, you remember, so we said that a function is, to just recall, that f going from some Rd to R is convex if for all u and v in Rd, we have that f of and all alpha between 0 and 1, we have that f of alpha u plus 1 minus alpha v so f of alpha u plus 1 minus alpha v is less or equal than f alpha f of u plus 1 minus alpha f of v. So that was our definition of a convex function, and we saw that several functions are convex and so on. But what I'm saying is that the notion of convexity depends on our ability to take elements of the domain and multiply them with constants and add them together. So the domain must be a vector space. So this is only relevant over vector spaces. Otherwise, we don't have this definition of convexity. And we'll have to remember it because we'll somehow need to translate our learning problem into problems of search over vector spaces. OK, so far this is just kind of the motivation, the direction in which we are going. And now I'm going to define the first two new definitions. So the first definition is a notion of a convex. What is a convex optimization problem? So convex optimization problems. These are problems as follows. So you are given some domain set A, say, W subset of Rd for some D. And the function f that goes from Rd to R. This is a convex optimization problem, so that's your input. And what we want to find, your task is to find the task, find some W in W such that for all U in W, f of W is less or equal f of U. So it's a problem of minimizing, finding a minimizer of the function f over the domain W. Right? And this should look kind of, you should notice the similarity with the problems we're discussing here. So this is a convex. This is an optimization problem, and when is it convex? So such a problem is called a convex optimization, problem if 1 W is a convex set, and 2 f is a convex function. So this is in general a convex optimization problem. Yes?
What were the properties of convex sets again?
OK. So let me just, so we have here the definition of what's a convex function. And a convex set, I don't even have to give you the formal definition. Just let me remind you with a picture. A set is convex if for any 2 points in the sets, the whole linear segment that connects them is contained in the set. OK? So this is a convex set. Is this set convex? No, because I have those wiggles here. OK, so a set is convex if for every 2 points in the set, the line connecting them, the linear segment, is inside the set. So we had the notion of a convex set. We have a notion of a convex function. And the convex optimization problem is trying to optimize the convex function over a convex subset of Rd. And it turns out, and this is kind of orthogonal to what we're doing in the course, that in optimization theory, there are lots of tools to solve convex optimization problems. So once we translate our problems to convex optimization problems, we can rely on a whole body of tools that was developed in the community of optimization. So I will not get into how this optimization is doing right now. What I want to talk about is when do learning problems turn into convex optimization problems. So if we want to connect it to learning problems, we have to recall what is a general definition of a learning problem. So just recall our general learning framework. And what do I mean by general learning framework? This is not necessarily learning a classifier with a counting number of errors, but it could be more general. So what is our input? So a general learning problem is defined by a triple. A general learning problem is a triple that contains of some class of hypotheses or models that you want to use. It contains some domain Z and some loss function L. So H is a class of models or hypotheses, and Z is our domain set, and L is a loss function. So L is a function that goes from H times Z to R plus, and this is a loss function. And the goal of the learning, so the goal of the learning, we have some unknown. We're given such a triple, so given such a triple, a triplet, and a some unknown, so it's not given to the learner, probability distribution P over the domain over Z. The goal of the learner is to use an IID sample S generated by P to find H in H with small expected loss. So what is this small expected loss? L P of H is the expectation over Z sampled from P of the loss of H with respect to Z. That's what we want to minimize. I mean, we have mentioned this general framework at the beginning of the course. And everything that we've done so far can be cast in terms of such a learning task. Yes?
Can we consider learners that return
Right. So here, that's a very good question. The question, I mean, we considered learners, when we talked about learning a class H, we considered learners that do not necessarily output a member of H. But in order to define the loss, let us assume that our H is the class of all potential functions that our learner can output. Yes?
Shouldn't it be SCP, not CP?
No, I mean, you use S, you use the sample S, but what you want to achieve is a hypothesis that behaves nicely with respect to the next point.
Doesn't tilde notation mean draw?
Drawn according to P.
Okay.
So Z is one point drawn according to P.
Small z, not. Okay.
That's small z. That here is small. I mean, the algorithm takes S as input. But the goal of the algorithm is to find some H which has small expected loss. So let me just remind you how we connect it to things that we have done. What can we do here? I don't know how much better this is. What? No, it's okay. Thank you. Okay, so just here are some examples that we have considered. So we will see that what we have done so far is really falls into this framework. So the most natural example is binary. So example 1, binary classification with 0, 1 loss. So what is binary classification with 0, 1 loss? So here we have Z is some pair X cross 0, 1, or any pair of labels, 2 labels here. So Z, small z, is each time a point and label. And H is a class of functions. Each H going from X to 0, 1. And finally, L, the 0, 1 loss, L0, 1. When we take a classifier H and the labeled point X, Y, what is going to be the loss? The loss that we've discussed so far, what is it going to be? Yes?
It's 1 when h of x is not equal to y, and 0 when
Right.
h of x is equal to y.
Right. It's going to be 1 if h of x does not predict y correctly, and 0 if h of x predicts y. So these were the problems that we usually looked at. So our sample S consisting of elements of Z was a sequence of such pairs. And this expected loss was just the usual expected error of our classifier H. So that's the example that we've been focused on so far. And this is the type of learning for which we had all our results. The fundamental theorem, VC dimension, they all talk about this framework. But as we mentioned when we discussed it in the beginning of the course, this framework is much more general. So it contains many more types of problems. So example 2 is the problem of regression. For example, linear regression. So what is the problem of linear regression? Again, I have to tell you what are those 3 components. So H is the family of all the class of linear functions h goes from some rd to r, and h is determined h of x. So h is determined by some vector w and some b, and hwb of x is the dot product w dot product x plus b. So this is just a linear predictor. So we have some phenomena x. We want to predict it. We're trying to predict it with a. And now z, my space z, is the space rd plus 1. So my examples can be thought of as pairs x and y, where y is a real number. So now what we have is not, so we can think of it as rd times r. So you get pairs, which is an element x that has features and a label, but the label is a real number. And now our loss, so now we have to define the loss. That's a missing component. So the loss has to talk about take an h and some hwb, which is this is the type of our models, and it takes some point z, which is of the form x, y, but my x is in Rd and y is a real number. And I can talk about the square loss. So the square loss is of this is I apply this w dot product x plus b, and I see how far I am from y, and I take the square. So this is called the square loss. So we mentioned this last time. Pictorially, what we have here yes.
The notation is a little different than I'm used to. Is this the same as the regression or the residual sum squares?
Right.
Yeah. Okay.
Yeah. So we can think of it like this. You have here, this is my x's, this is my x-axis, this is my y. So here x is just one-dimensional, and I have a collection of points here. And my hypothesis is some line h, which is determined by some slope w and the b here. So this h is determined by some w and b. And we can see that this loss is actually for every point x. What do I look for in the loss? So if I have here a point x, if I have here a point which is the form x, y, what is the loss of this point? So I substitute x in my line. I see what I get here. I look at this difference between, because this is y. So I look at the difference between, so maybe I'll draw it on a point which is further away from the line, so we will see more clearly what is happening. So this is a point x, y. So this is my y, and this is my x, right? What do I have here? Here I have h of x. This is h of x. But h of x is just this function. This is h of x. So I look at the distance h of x minus y. I look at the misclassification here, by how much did h of x miss the y that I had here, and I take the square of this. So this is my loss on every point. I'm trying to minimize the total square loss, the expected square loss on a new point. So that's linear regression. So linear regression falls naturally into this framework. Is it clear? So linear regression falls naturally into this framework. We have h of x. Our input was the point xy. My loss on the point xy is the difference between the prediction h of x and the y that I got as input. And I square it. And We mentioned other learning problems. I will not even elaborate, but we saw that this can also describe other types of problem like k-means, clustering, where here your space Z is just a subset of Rn, and H is just the points, the k-tuples in Rn, so it's Rn times Rn times Rn k times. And what you're trying to minimize, so I'm trying to find a k-tuple that I will call of centers mu1, mu2, up to mu k, such that with respect to my distribution, every point is pretty close to one of the centers. So the loss, when I get such a k-tuple, mu1 up to mu k, and I get a point x, is the minimum over I between 1 and k of the distance x minus mu I squared. So for every point, the loss of the point is how far is it from the closest center. Right? So these are my centers. I want to choose centers such that every point will be close to at least one of them. So my loss, after I have chosen a set of centers, is the minimum distance between the point x and the closest center, the minimum over all I between 1 and k. So this problem, you can think of it, say the problem that you are trying to find locations for pizza shops, and you have a population of customers, and you want to minimize, you know that you can just create k pizza shops, and you want to minimize the expected distance between a customer that orders a pizza and the closest location from which you will deliver the pizza. Right? So mu1 to mu k is where I located my k pizza stores or pizza bakeries, and I get a point x. The loss is the distance of this x to the closest shop, because that's how far I'll have to drive to deliver it. And again, it's the same kind of setting. There's some unknown distribution over the population where the x's are living. We can see a sample, and based on a sample, we try to find centers that will minimize the expected distance of a customer from its closest shop. So what I'm saying is that this general framework captures many types of problems, and so far in the course, we mainly focused on the 0-1 problem. So now let's go back to and connect it. Unless there are questions at this point, I will go back and connect it to convexity. And all of those problems are learning problems that can be solved with the same tools. OK, so let's connect it to convexity. So we want to define, we have a definition of a learning problem, and we have a definition of a convex optimization problem. Now I want to define what is a convex learning problem. So a learning problem is a convex learning problem. Oh, it's not good. LP has too many meanings. So a convex learning problem So a learning problem for us is such a triple. So a learning problem contains of H, Z, domain Z, and a loss. Right? All the examples that we saw here, this is a capital Z. If the following two conditions hold, one is that H is a convex subset of RD for some D. So note that now I'm talking about learning problems where my hypothesis is always parameterized by a vector in RD. But we've seen such problems, like 0-1 classification. If I want to classify with a half space, I can parameterize the half space by weights. Or if I want to do linear regression, naturally, my hypothesis is a line which is parameterized by weights. So I'm talking now only about problems in which I can view H as a subset of RD. And two, for every Z in Z, the function L of, now I'll put here my H, or some W, Z is a convex function. Yes?
This might be a silly question, but for H to be a convex subset of RD, does that mean every element in H is a convex function?
No. H, okay, so yeah, this is a good question because it points to some potential confusion. H, for me, is a subset of RD. So it's not a set of functions. Before we talked about H's, which were functions from X to 0, 1. Now I not view H as a set of functions, but I view H as a set of vectors. So this is a good point to note. Here my H is a subset of RD. So H, let me just, so it's convex, is convex as a subset of RD. So the most simple example is if I want to do classification. So examples, no, the generic example is that every H in H is a linear function, a homogeneous linear function H of W, and H of W of a point X is just the dot product Wx. So I can view H as a set of all W's. As a set of W's is a convex subset of RD. Yes?
So H is kind of the parameter space of whatever.
Right. H is our parameter space. It's a space of parameters. Very good. A very good notation. So H is a parameter space. So these are the parameters. This is the parameter space. And every function in H is identified with its set of parameters. Yes?
Why don't allow H to be just a generic convex set?
I didn't define convex sets. In order to define a convex set, I need the linear structure. Because a convex set is defined by addition and standard multiplication by a scalar. So without loss of generality, convex sets are defined over subsets of RD. Because we need a vector space. So the only loss of generality here is that we miss infinite dimensional vector spaces, which we don't need to discuss here.
Unlike convex, would that be,
What?
if R was replaced with C, would that be isomorphic to R?
So there is a theorem that every finite dimensional vector space is isomorphic to over R is isomorphic to RD. Okay? So this is general enough for us. Yes?
For the last line on the third,
Right.
is that L of a
Okay, so that's a very good point. What do I mean by this? I have here a dot. And the dot, what I'm going to have here is W. I want to tell you that when I tell you that L has two parameters, it has H and Z, right? And when I tell you it's convex, we talked about convex functions of one parameter. So I wanted to emphasize which parameter is the parameter that I'm talking about. I'm fixing Z, and once I fix Z, the loss becomes just a function of the H that I will put here. So as a function of H, I want it to be convex. Okay? But that's a good point. I mean, this notation just means I had here a two-parameter function, but when we talked about convex functions, they had only one input. So, but if we fix Z, it becomes a function of one input. And as a function of this input, I want it to be convex for every choice of Z. So our H's will be, we will look at them as subset of RD, and we'll mainly, for concreteness, we'll focus on the situation where these are the functions that we are trying to learn. Linear functions, homogeneous linear functions. So just note that the examples 0, 1 classification zero one classification and linear regression, zero one classification with a class of half spaces as well as linear regression can be viewed as having H as a subset of RD. Because if I'm trying to classify or to do regression with a linear function, then I can just view my class of classifiers, my set of classifiers, as a subset of RD. Every classifier is determined by its parameters. Okay, so the next thing is, so we defined what is a convex learning problem, and we see that it gets very close to the notion of a convex optimization problem. Now, which of the problems we've discussed so far, which of these learning problems are convex learning problems? So my first claim is that if L is a convex loss, then and H is convex, is a convex subset of RD, then for every sample S, ERM H with respect to S is a convex optimization problem. So here we connect our learning to convex optimization. The task of finding the minimizer of the empirical risk is a convex optimization problem. Why is this a convex optimization problem? Because what is it that we want to optimize? Yes?
We want to minimize the error over the sample, which is supposed to be representative of the error of the distribution.
Right. So the task given S and H, given S, H, and L, the ERM task is to find H in H that minimizes LS of H, which is 1 over the size of S, the sum of all Z in S of LHZ. Right? So ERM, I have a sample. It doesn't necessarily have to be a 0-1 loss. ERM is saying I have a sample S. I want to minimize the average loss over the sample. I look at all the points Z in the sample. For each of them, I have some loss. It could be whether I predicted correctly or not. And I want to optimize the average loss over the sample. Now, why is this a convex? What do I need for this to be a convex optimization problem? For this to be a convex optimization problem is, first of all, I have to find, I'm searching for a H in H. So the search is over the space H. This set has to be convex in order to be a convex optimization problem. But how do I know that it's a convex? Because we assume that our class H is a convex subset of Rn. What is the other component that I need for this to be a convex optimization problem? Yes?
You need to show that LS of H is convex.
Right. I need to show that this function is convex. Now, what did I assume? I assumed that this is a convex function of H. We assume that for every Z, this is a convex function. So why is the sum, the normalized sum, why is it the average? Why is it a convex function? Right, you have to look at the notes from last class. So in the notes of last class, we showed that, just recall that if for all I between 1 and m fi of W is a convex function, and then for any weights, so I will not use W here because it may be confusing. So for any A1 up to AM which are greater or equal than 0, the function f of W equals the sum over I goes from 1 to m of AI fi of W is also convex. So this is one of the closure properties that we have talked about last time when we discussed convex functions. So this is something we showed last time. But now we can apply it to this sum. Because we have here S, which was Z1 up to Zm. And this sum, I can rewrite it. So Ls of H is just the sum over I goes from 1 to M of what is going to be my coefficient? Yes?
1 over the size of the sample.
Right, 1 over the size of the sample. And here I have L of H Zi, which I know is a convex function because we assume that for every choice of Z, this loss as a function of H is a convex function. So if my loss is a convex function and the class H is a convex subset on Rm, then ERM becomes a convex optimization problem. So in such cases, we will be able to implement ERM efficiently. OK, so let's now use this new feature of learning problems to examine learning problems that we have already discussed before. So we have looked at learning problems. So let me start with the two examples that we examined before. So example 1, what happens with linear regression? So if we allow linear regression, allowing our parameter space to be RD, that is, I allow all vectors or the ball over the set of all W in RD such that the norm of W is at most 1. This is also common. So I'm trying to do regression where my coefficients are any set of real numbers or any set of real numbers such that its norm adds up to 1. I mean, we don't have to worry about this, but this is a more common search. Now, what is my loss? We have already noticed L, the loss of such a W on a point Z, which is xy, which is defined, we have seen the definition, is as Wx minus y square is convex for every pair xy. That is also something that we've seen last time. So the conclusion that if we're doing linear regression, ERM, trying to find the line that best fits this training sample, is a convex problem. So the conclusion is linear regression with square loss is a convex problem, a convex learning problem. That's it. I mean, all the course so far, we didn't talk about regression. We talked about classification with 0-1 loss. So just by the fact that my first example is not the example that we've been discussing all along, you can already guess what is the answer about the 0, 1 loss. Is it going to be convex or not? We have many indications for this answer. So example 2, learning half spaces, learning linear classifiers with the 0, 1 loss. This is what we've been doing so far in the course. So what is your guess about this example? Is it going to be convex or not? No, why not? Yeah, I mean, one indication is just why didn't I start with this example if I was doing it all along the course, right? But we have even stronger indications.
If you graph your loss, right, you get this kind of...
Yeah, but it's not yet. Okay, so we will see exactly why it's not convex. But another indication that you could have to the answer here is that we said that this task is NP hard to optimize. And we said that if we get an convex optimization problem, we know how to solve it efficiently. But, OK, so why is it not? So this is not convex. So let me just show you an example why is it not convex. It's not a convex optimization problem. So where can it break down? So I claim that L, the loss of, what is the loss of, I have a half space, say homogeneous half space W, and I get an input point x, y, which is some point in Rn and label 0, 1. And the loss was defined, the 0, 1 loss. The 0, 1 loss was defined, let us recall, it is just 1 if. So what was the loss here when I did linear classification? When did I have 1 and when did I have 0?
1 if y is greater than w of x.
Yes.
HW of x is not equal to y.
HW of x, but what is HW of x?
It's the function that maps x to 0, 1.
So how do you do it?
Parameterized by w.
Yeah. OK, I want to just recall what it is. It is 1 if the sign of wx is different than y, and 0 otherwise. And we can also write it, it's the same as saying that this is 1 if y times wx. If they don't have the same sign, what do I know about the multiplication of y with wx? Yes? It's negative. It's less than 0, and it's 0 if y times wx is greater or equal than 0. OK, so let us just see. So this function, we already suspect that it's not a convex function and that the ERM task is not convex. Let me just show you an example of why, indeed, the ERM is not convex for learning half spaces. So we're trying to learn homogeneous half spaces. And we have to realize what is, we want to look at the loss. Right? So we want to know if the loss of, we want to check if the loss of alpha times W1 plus 1 minus alpha times W2. I want to compare this loss. Is it less or equal to alpha times the loss of W1 plus 1 minus alpha. And OK, so this is the loss. This is the loss with some x, y, with respect to some x, y. And everything is a loss with respect to some x, y. So it's alpha times the loss of W1 with respect to x, y, plus 1 minus alpha, the loss of W2 with respect to the same x, y. That's the loss on a point, and then we can extend it to the loss with respect to some sample S. So we want to check the same thing with respect to a sample. So let us just look at what is this vector? Alpha W1 plus the W2, and what is the loss on the sample? So let us look at a concrete sample. So let us look at a sample that looks like this. So let us look at a sample that looks like this. Here I have positive points, and here I have negative points. OK? So this is my sample. What I drew here are the points and their labels. They are negative inside the pizza slice, and they are positive inside the pizza slice, and they are negative outside. And assume that I have many more points here. Sorry. Here I have lots of points. So here it's very dense. And now I want to consider two classifiers. So my W1 will be this classifier. This will be my classifier W1. And this will be my classifier W2. So what is the loss of W1? This is my classifier W1 says this is plus and this is minus. What is the loss of W1? Let us just completely erase the points here. So what is the loss of W1? Which points, in which area do I have the points on which W1 mispredicts? Yes. So where does it mispredict? So let me mark the areas. Let's call this area A, B, this is area C, and this is area D. So in which areas does W1 mispredict? On B. W1 mispredicts on B. And you see, on B it mispredicts because everything above is plus. W2 mispredicts on which area? Where does W2 mispredict? Yes, on D. OK, now I want to look at the combination. So what is going to be the vector W1 plus half W1 plus half W2? Where is this vector going to lie? This is W2, this is W1. If I take the average, half W1 plus half W2, I'll get this vector. This is half W1 plus half W2. Because W1, I mean, it's not difficult to see. This is just the average between those two vectors. This is the vector W1. This is the vector W2. I take the average, I guess this guy. Now, this vector what is the loss of this vector? In which areas does this vector miss? Yes. On which regions does this guy make a mistake? Yes. Both B and D. So W1 only mispredicts here. W2 only mispredicts here. The combination mispredicts on both B and D. So the loss of half W1 plus half W2 LS of half W1 plus half W2 is the size of B plus the size of D divided by the total number of points, where the loss on S of W1 is just the size of B over M, and the loss of S of W2 is just the size of D over M. So if we assume that B and D, so just assume B equals D. So what I'll get here say B equals D, B equals, say, a third of the points. A third of the points are in B, a third of the points are in, or a quarter of the points. It doesn't matter. A quarter of the points. So now let us just compare what we need here. The loss with respect to S of half W1 plus half W2 is going to be how much? It's a quarter plus a quarter, so it's going to be a half. But half the loss with respect to S of W1 plus half the loss with respect to S of W2 is going to be half times quarter plus half times quarter, which is just a quarter. So this loss is, did we get it right or did we get it the opposite way? What? Yeah, we got it right. So the loss, we're looking at the loss. So this is the function Ls of W. And I have here W1, I have here W2. Each of them has loss, which is a quarter. But if I look at the loss of the average between them, the loss of the average is a half. So if I look at the point W1, half W1 plus half W2, so here I had a loss quarter, here I had a loss quarter. At half W1 plus W2, I got a loss which is a half. So at this point, I got a loss which is above the average of these losses. So the function is not convex. A function is convex if you have two good points. You take the average, you cannot get worse. You do at least as good as those two endpoints. And here we had two pretty good points. Each of them had error only a quarter. We took the average, and the error blew up to a half. So this function is not convex. OK, so the 0-1 loss is not convex. So if you want to do 0-1 classification, we need to change the problem somehow. OK, so how do we solve it? So our conclusion is that the 0-1 loss conclusion, and we saw it from several aspects, but we saw an example, the 0-1 loss is not convex. And therefore, doing ERM, and we also saw that, furthermore, ERM S over the class H of linear classifiers with 0, 1 loss is not a convex optimization problem. And that's the source of our computational trouble. So we would like to overcome it. And how do we overcome it? We overcome it by basically cheating. So this is one of those points where practice begins to diverge from theory. I mean, the theory tells you this is not convex, this is what we want to minimize. We want to find a half space that minimizes the error. But the problem is too hard. So now we are trying to make some kind of tweaking of the problem so that the problem will be solvable. And the notion that we introduce here is the notion of surrogate loss functions. So this is a very useful notion in the practice of machine learning. Our natural loss function is not convex. We are introducing a notion of a surrogate loss function. So what is a surrogate loss function? So L. So we assume we just focus. We focus on learning with linear functions. It could be either prediction or regression. So H is a subset of RD. And we can assume that H is convex. And we say that the loss L is a convex surrogate loss if two conditions apply. One of them is that L W Z is a convex function for every, let us look at the case Z is xy, so let me write here xy. For every xy, it's convex loss function. And second, that for every xy, my L of W xy is greater or equal than L0, 1 loss of W xy for all W in H and all xy. So we want to replace our loss with a convex loss that bounds it from above. Pictorially, we can draw it like this. So if here we have the loss of Wx y, so it's the loss of Wx on a point y, and here I have y times Wx. The 0, 1 loss, how does the 0, 1 loss behave? The 0, 1 loss gives me, as long as this is positive, the loss is 0. And the minute it becomes negative, the loss becomes 1. So that's the 0, 1 loss. The 0, 1 loss for a linear predictor. We look at y times the prediction, times the sign of the prediction. If they have the same sign, it means that the product is positive. Then we have 0 loss. If they have different signs, the product is negative. We suddenly have 1 loss. And a convex loss function will generally look like this. It will generally look like something like this, which will be, so this is going to be my new function, L, the L of W on the point xy. My new loss is going to behave in a convex way. It's going to be a convex function. And this convex function is going to upper bound the 0, 1 loss. At every point, it's above the 0, 1 loss. And we'll discuss, we have time to discuss only one common surrogate such loss. The most common surrogate loss is going to be the hinge loss. So there are two things that I want to do in these 2 minutes. And this is to introduce the hinge loss, but also to discuss what is the resulting problem. So let me postpone the hinge loss to Friday and just consider the resulting problem. So the resulting problem is that, so now the learning problem, we have the new or revised learning problem. Find H in H that minimizes the new loss, L surrogate of H over my distribution. That's going to be my new learning problem. Yes?
I mean, that could be different though, right? Like, is there anything that says that the loss where, so for example, in the 0, 1 loss, when you're above 0, then the loss is 0, right?
Right.
So is there anything to say that the loss has to be correspondingly lower? Like, you drew a line here, but couldn't the line go up again after it hits the, when it becomes positive? And it would still satisfy the condition?
The condition is that I want this new loss to upper bound this loss.
Right, but it could
And to be convex.
And to be convex.
Right.
Okay, but
So in order for it to be convex, in order to upper bound, it has to pass through this point.
right.
In order to be convex, it couldn't go down sharply.
Couldn't it? Well, I guess if it's can it go back up again?
We're here.
Yeah.
If we go back up again, right, but then we want to minimize the distance between them. We want to be in a situation where minimizing the surrogate loss is as close as possible to minimizing the 0, 1 loss that we care about. Right.
So we choose
We choose the surrogate that is as close as possible to our 0, 1 loss that we care about, but is still convex. Okay, so this is as much as we can do today. We are out of time. We'll continue Friday. Remember to bring devices that you can connect to the internet with for the evaluations. People who haven't picked up the assignment 2 can do it now. And see you on Friday.